information is in the notes that I'll post after class. There was also one other organization that asked me to share some information. So Delta Omega Chi, which is one of the many pre-health societies that I can't keep track of on campus, but one of them. And they're in collaboration with a bunch of other ones for this event. They're having a health panel. So if you're still undecided about whether you want to get involved in healthcare in the future or which area that might best suit you, they have this event every year that it's it'll be Wednesday right after our class, and you can check that out if you're interested. All right, so let's get into what we're going to cover today, which is we are going to finish chapter 5 and probably begin chapter 6 at the end. So we are finally getting to a point where we're a little bit ahead of the homework assignments, which is after the long slog of the first part of the semester. So what we're going to talk about today is another concept related to stoichiometry, which is the concept of limiting reactant or limiting reagent. I don't have a formal slide where I'm going to define this, but basically the idea here is that in the problems we've done so far, we would just give you stoichiometry problems, which we covered last week. We'd give you the amount for one reactant or one product, and you would figure out how much of the other reactant do you need, or how much of the other product is formed, and so on. But sometimes when you do chemical reactions in practice, you're going to take two reactants and mix them together, and they're not necessarily going to be in the exact right ratio to react completely. So if they're not in the exact mole ratio that the balanced reaction dictates, then there's going to be some reactant that's left over. So a way to think about this is sort of a cooking analogy. So let's say you wanted to bake something that required 2 eggs and 4 cups of flour, and you have on hand 4 eggs and 4 cups of flour. So you have enough eggs to bake 2 of these items, but you don't have enough flour, so the flour is going to limit how many you can actually bake. So same thing sort of happens in chemistry, where if you mix 2 things together and they're not in exactly the right ratio to react with each other, then there's going to be one that's in excess, which has left over, and then one that's called your limiting reactant, which is going to limit how much of the product can form. So when you're doing problems like this, first let's just talk about how you figure out what the limiting reactant is, or how you approach problems like this. So in a limiting reactant problem, we're going to give you amounts of 2 or more reactants. So in the previous problems we did, we just gave you the amount for one reactant, and you started from there. In these types of problems, as we'll get to a little bit more detail later on, the way that you recognize that you need to do these extra steps is that we're going to tell you you have this much of one reactant and this much of a second reactant. And so before you start the problem, you need to know what the limiting reactant is. Now, the way that the book does it, which is fine, but sometimes takes a little bit of extra time, is you're basically going to do the problem twice. So the way that you have that the book prescribes that you do this is you determine the moles of each reactant, and that's going to typically be the first step in any stoichiometry problem, is to determine moles. But what you're essentially doing, if you follow the book's approach, which works, is you're just going to do the problem twice, once for each reactant. But I think this approach, sometimes it's a little bit hard to keep straight what the numbers mean at the end of the day. And so then what you're going to do is, and I think this is where this approach starts to get a little bit confusing, is you're going to determine, so if we have 2 reactants, A and B, you're going to determine how many moles of B are required to react with however many moles of A that you have. Okay, so you figure out the amount of each that you have, and then you're going to do a stoichiometry calculation where we figure out, well, how many moles of B are actually required to react with the amount of A that we have, using the balanced reaction, the balanced stoichiometric coefficients, and all the stuff that we covered last time. And we'll give examples, but I'm not going to usually use this approach. So if you want to learn this approach, you can practice it on your own and read the book, but I'm not going to go through it this way. But I just want to introduce it to you if you do like to follow the textbook or you think this approach is better. So then you're going to calculate how much B is required to react with however much A you have. So if the amount that you calculate is less than the actual amount of B, that means that A is a limiting reactant. So you're going to calculate an amount, and you're going to compare it to the amount of B that you actually have, that we're telling you that you have in the problem. Now, I think it's easy to trip yourself up with this approach. That's why I don't like it so much. But it works. So if you calculate an amount that is less than the actual amount of B present, that means A is a limiting reactant, or vice versa. And so basically the idea here is if you calculate an amount of B that's less than what you actually have, that means you have actually more B than you need, meaning A is the limiting reactant. But if you calculate an amount of B that's greater than the amount of B you actually have, that means you don't have enough B and it's the limiting reactant. All right, and this works in sort of both directions. So this is one way to do it, just calculate moles of each and work both ways. The way that I do it, which I think is less confusing, perhaps not necessarily less work, is the way that I was taught in the ancient times when I took a general chemistry course, which is an approach called what's referred to as the stoichiometric ratio. So what we're going to do for each reactant in the problem is we're going to determine what's known as the stoichiometric ratio, or at least that's a term that we can use for it. Now, the advantage of this approach is that it basically allows you to clearly and unambiguously define what the limiting reactant is, because as we'll cover in a little bit, once you know what the limiting reactant is, any other stoichiometric calculation you do for that problem, whether you're calculating an amount of a product that forms or an amount of another reactant that's needed, any calculation has to start with the limiting reactant. So we need to identify what it is so that we can proceed to the rest of the problem. And this approach allows you to do that in a very sort of straightforward way. So what we're going to do is we're going to determine the stoichiometric ratio for each reactant, and let's define what that is. And so basically what the stoichiometric ratio is, which I'll abbreviate as R, capital R, it's going to be the moles of that reactant. So this still involves moles, as does everything in stoichiometry. And then we're going to divide that by the reaction coefficient. So you need a balanced chemical equation, as we always do for stoichiometry. And the ratio of these two, moles of the substance to the reaction coefficient, is what I'm going to call the stoichiometric ratio. And so you're going to do that for however many reactants you have, usually only 2, sometimes 3, depending on the type of problem. And then the reactant that has the smallest stoichiometric ratio is the one that's the limiting reactant. So basically, as I said, you can very quickly identify what the limiting reactant is by just comparing the different R values that you calculate and identifying the smallest. All right. And I will frequently use the abbreviation LR for limiting reactant in case it's not obvious. So that's how you do it. Now and then the key point, as I already referred to, is that any subsequent calculation you do is going to start with the limiting reactant. So whatever the problem's asking you to do, whatever it's asking you to calculate, you need to start with the limiting reactant, because the limiting reactant is going to limit, as the name implies, how much product can form and how much other things react in this. So any substance stoichiometric calculation starts with the limiting reactant. So we'll go through a few examples to see how exactly this works in practice. The one word of caution that I have, which I will remind you about frequently, is that the one sort of, it's not a detriment, but a danger of this approach is you're going to use the stoichiometric ratio R to figure out what the limiting reactant is, and then after that, that number is completely useless, okay? So you don't want to use R for anything else afterwards. You're going to use it to figure out what your limiting reactant is, and then you're going to throw it away and never use it again. So a lot of people start trying to do calculations starting with R. Sometimes you get lucky and that works, but in reality it's a relatively meaningless number, and we don't want to actually use it anymore after we've identified what the limiting reactant is. From there, we're going to go back and usually start with moles of limiting reactant to proceed forward to whatever other things we're trying to calculate, okay? So just be careful not to overuse this stoichiometric ratio. It's just a way of determining what the limiting reactant is and doing that in a pretty quick and easy way. All right, so then to sort of wrap this up in sort of the more general terms before we get into some examples, the question is, how do I know if I need to determine limiting reactant? Because all the problems we did last time, this wasn't an issue. We just started the problem, no big deal. We didn't care what limiting reactant was. And so the dead giveaway is that if you are given amounts of 2 or more reactants, you have to figure out which one of those is a limiting reactant, okay? So we didn't see any problems like that last time, so we hadn't learned this yet. But in the problems where you're given amounts of 2 or sometimes more than 2, but usually only 2 of reactants, and amounts can be masses, moles, other quantities we'll learn in the next chapter that are related to moles as well. So if you know the exact amount in any unit, in any quantity of each reactant that you have to first figure out which is the limiting reactant. All right. So you could get lucky and guess, but I wouldn't recommend that because you have a 50% chance of being wrong if we give you two reactants and you're just trying to guess what the limiting reactant is. So make sure you do the proper steps using either approach that I've outlined today to make sure you know what the limiting reactant is, and then you know what the correct one to start with is when you're doing your calculations. So that's when you need to figure out what the limiting reactant is. In other types of problems, like the ones we did last time, we just either give you one amount of a reactant, let me reword this. If you're given an amount for only one reactant, and sometimes in problems like this, we would say, reactant A is combined with an excess amount of reactant B. So if we explicitly tell you that one of the reactants is an excess, then you know which one is limiting because that's what's given in the problem. But in most cases, we'll just give you an amount for only one reactant, and if that's the only amount you have to assume that that's the limiting reactant. There's no other way to do it. So if we give you the amount for one reactant, or in some cases, we'll start problems with an amount of a product. So in some of the problems we did, I don't know if we had any exactly like this last time, but we might say how much of reactant A is required to form this many grams of product. Well, in that case, you don't really care what the limiting reactant is because you're not dealing with quantities of two reactants. You're just given, okay, we want this much product, how much reactant do we need? So if you're starting with a product amount as sort of your given information in the problem, then you don't have to worry about limiting reactant. So again, it's only when you have amounts of two or more reactants do you need to consider this. And so in these situations, you can just start the problem. You don't have to take any extra steps to figure out limiting reactant. All right, but in other problems where we give you amounts of two reactants or more than two reactants, it's important to know what the limiting reactant is. All right? All right, so that's a common point of confusion, at least early on when learning this. And so now that we have that recognized, let's look at some typical problems. There's some cosmetic changes that I made in the notes, so don't be confused by it. I'm starting to replace those script M's with MW because our book doesn't use the script M abbreviation. So if you printed out the notes from Blackboard, it might look a little bit different than what I have here. I have script M instead of MW. They mean the same thing, but I'm just going to try to go to a more consistent notation that's more aligned with what your current textbook has. All right, so don't be thrown off by that. It's the same numbers, same problems. And so what we have here is we gave you a balanced chemical equation. Ammonia reacting with fluorine to make dinitrogen tetrafluoride and hydrogen fluoride gas. And we want to know how many grams of N2F4, the product, can be obtained from the reaction of 5 grams of NH3 with 15 grams of F2. So in this problem here, we gave you the amounts of both reactants, 5 grams of ammonia, 15 grams of fluorine. So we know how much of each we have. We have to figure out which one of those is the limiting reactant. And so there's going to be some extra steps involved. And again, the way that I like to do this is we'll first start out by determining the moles of each reactant. This is part of what we have to do anyway in the problem. So for NH3, it's just going to be a mass to mole calculation like we've been doing. We have 5 grams of NH3, 5.00. And then we gave you the molar mass, which is 17 grams per mole. And so it's going to be 1 mole of NH3 has a mass of 17.0 grams. So grams cancel out. That gives us moles of NH3, 0.294. Now we're going to find the moles of the other reactant, which is F2. We have 15 grams. And we're going to use its molar mass in the same way. 1 mole of F2 has a mass of 38 grams as we're given in the problem, where we could calculate easily. And so we get 0.395. Now remember that just determining the moles of each reactant does not tell you what the limiting reactant is. Moles by itself doesn't do that. We have to go through and we have to figure out the stoichiometric ratios for each of these. All right? So once we have moles, we can easily determine the stoichiometric ratio, as I abbreviated it R before, by dividing by the coefficient for each of those reactants. All right, so the ratio for NH3 is the number of moles that we have, 0.294, divided by the coefficient in the balanced equation. So the coefficient in front of NH3 is 2 in the balanced equation up here. So we're going to divide that number by 2 to get an R of 0.147. Then we're going to do the same thing for F2. We're going to take the number of moles of F2 that we have, which is 0.395, and we're going to divide it by its coefficient, which is 5, in the balanced chemical equation, and we get 0.0790. And the smaller of these two numbers is going to be the one that's our limiting reactant, which clearly is F2. So this number is smaller, so that's our limiting reactant. Now remember that that number now is no longer useful, but it allows us to identify that F2 is limiting reactant. And so any other calculation we're going to do in this problem is going to start with how much F2 we have. I like this example too because it shows us two things. First of all, if we want to know what the limiting reactant is, we certainly cannot just look at the masses of each one. There's 3 times as much F2 in terms of mass, but it's still the limiting reactant. We also can't just look at the number of moles that we have. We have more moles of F2 than NH3, yet F2 is still the limiting reactant. So if you're going to identify the limiting reactant in this way, you have to calculate the stoichiometric ratio by taking the number of moles and dividing it by the coefficient. That, in this case, is the only way that you're going to figure out what the limiting reactant is. So now that we know that F2 is the limiting reactant, we're going to now do the calculations, and any calculation we want to do is going to start with F2 as our starting point. So we're going to do the calculation that we're asked to do, and we're going to start with the amount of F2 that we have. All right. So what we're looking for in this problem is how many grams of our product N2F4 can be formed. And we're going to start with the amount of our limiting reactant. Now we have here the mass of limiting reactant, but we already calculated moles in the previous slide, so we can just start with moles of limiting reactant and save ourselves a step. So we have 0.395 moles of F2. We could have started with the mass of F2, but we would just be repeating a step that we already did, so there's no need to do that necessarily. And then once we have moles of limiting reactant, we can figure out the moles of product that form by using the coefficients in the balanced equation. So we want moles of F2 to cancel out, and we want to convert into moles of the product N2F4. And what we can see is that N2F4 has no coefficient, so a coefficient of 1, and then F2, as we saw before, has a coefficient of 5. So that gives us moles of N2F4. This is asking for grams, so we're going to now use the molar mass of N2F4 to convert grams into moles. So we want moles in the denominator to cancel out, grams in the numerator, so we're going to multiply by the given molar mass of 104.0 grams per mole. So that's going to give us now mass of N2F4, which is what we're looking for, and we'll get 8.22 grams. All right. If you had instead started the calculations with NH3, you would have gotten a number that is larger than this and not the correct answer, because NH3 is the excess reactant. We need to use the limiting reactant to figure out how much product will actually form. All right, so any questions on those steps so far? Not missing anyone? Okay, big room, so sometimes it's hard to see you guys, so shout it out if you have anything. And then another question we can sometimes ask you then is, how many grams of excess reactant remain? So the concept of limiting reactant is that whatever the limiting reactant is going to go away completely during the reaction. It's going to be converted into the product. You're going to have 0 limiting reactant left over. But then whatever's not the limiting reactant is an excess reactant, and then there's going to be some of that left over at the end. So how do we figure out how much that is? So because F2 is the limiting reactant, that means the other one, NH3, is our excess reactant. So we're going to figure out how much NH3 is left over when the reaction goes to completion. So the way we do this is we're going to use, again, starting with a limiting reactant, we're going to use stoichiometry to figure out if we have that amount of our limiting reactant, how much NH3 will actually react with it, how much NH3 is required. And so we're going to calculate the mass of NH3 that's going to be consumed in this reaction using stoichiometric ratios. So we're going to start once again with moles of limiting reactant, which is 0.395 moles of F2. So as I said, any calculation is going to start with our limiting reactant, and same here. And then if we use the mole ratios in the chemical equation, we can figure out how many moles of NH3 are required to react with that many moles of F2. And so the ratios are 2 to 5. So we want moles of F2 to cancel and figure out how many moles of NH3 that requires. And so we're going to use these coefficients, 2 in front of NH3, 5 in front of F2. All right, so now we know how many moles of NH3 were consumed, and then we can use, again, the molar mass of NH3, which I gave you earlier, which is 17 grams per mole, to convert that back into a mass amount. So there's 17.3 grams of NH3 in 1 mole of NH3, and so that gets us to figure out how many grams of NH3 were actually consumed in this reaction. So the number that we get is 2.69, and remember that that number does not represent how much NH3 is left over. That represents how much NH3 reacted with the F2, the limiting reactant. So it's always important to keep in mind that this is the amount that was consumed in the reaction. So to figure out how much is left over, we're just going to do a subtraction. The NH3 that's in excess is going to be the amount we started with. So if you recall on the previous steps, we put in 5 grams of NH3. That was given to us earlier at the beginning of this problem. So that's our starting amount of NH3, 5 grams. We just calculated that 2.69 grams would react with the limiting reactant. So we're going to subtract that amount to figure out how much is left over. And so that difference gives us 2.31 grams, which means at the end of this reaction, there's still 2.31 grams of NH3 that have not reacted with anything. So all the F2 is gone. They can't. These remaining 2.31 grams of NH3 are just going to sit there because they don't have any more fluorine to react with. All right, so that's another little wrinkle we can now have, is recognizing what the limiting reactant is and that what else, anything else in there would be in excess. We can figure out exactly how much of the excess reactant will be left over, will not react at the end of the reaction. All right, questions on that step? Okay, so let's just do one more, which is, in this case, very similar, just a little bit more involved. So this time I did give you 3 reactants. So that's probably as high as we'll ever have to go. And so the first step in this question, we have N2O plus sodium plus ammonia, making sodium nitride, as it's called. Is that right? No, sorry, sodium azide. This is actually the chemical that's in airbags. If you shock it, it explodes. It releases N2 and explodes. So hopefully you've never experienced that in your everyday life, but it is out there. And then it's going to form also sodium hydroxide and nitrogen. Okay, so this is the chemical equation that we have for us. So again, fairly complicated, but everything's given to us. We don't have to worry about balancing it or writing it out. And so we have 5.25 grams of N2O, 4.05 grams of sodium, and 2.57 grams of NH3. What is the limiting reactant? So in this case, we have amounts of all 3, so we're going to have to do this for all 3. We have to calculate for each of the reactants moles and then stoichiometric ratio. So for N2O, we have 5.25 grams. We're going to convert to moles using its molar mass. So these steps should all be old hat by now. So the molar mass is 44. All right, so what we get is 0.119 moles of N2O. And then the stoichiometric ratio for this is that number, 0.119, divided by the balance coefficient, which is 3. All right, so these are sort of the first 2 steps we're always going to want to do in a limiting reactant problem, if you like this approach anyway, which is to calculate the moles and then divide the moles by the coefficient to get this stoichiometric ratio that will allow us to identify which one is limiting. Same thing for Na, sodium. So we have 4.05 grams. And in this case, we're going to just use the atomic mass of sodium, which is given, but we could also get it from the periodic table. 1 mole of sodium has a mass of 22.99 grams. And so what we end up with is 0.176. And then the stoichiometric ratio for sodium is that number divided by its coefficient, which is 4. And so we get a number that's a little bit bigger, 0.044. And then finally for NH3, we have 2.57 grams. So let me write that in full. So that's NH3, and then we're going to use the molar mass of NH3 to convert that to moles. Dividing by the molar mass to go from grams to moles. So we get 0.151 moles of NH3, and the stoichiometric ratio is that number divided by the coefficient, which is just 1 in this case. There's no coefficient, so it's 1. And so we get 0.151 also for the stoichiometric ratio. All right, so the one that's the smallest is the limiting reactant, and what we see is that it's this first one here, N2O, a little bit smaller than sodium, so this is our limiting reactant. All right, so in this problem, again, the one that has the largest mass ends up being limiting reactant, so we cannot simply compare masses. This one, we did see that the one with the least number of moles was our limiting reactant, but that's not a general outcome. We have to go through and calculate stoichiometric ratios, and only with these numbers can we compare these three and figure this out. So the limiting reactant is N2O, so that's going to be choice A in this multiple choice question. Okay? And then the next question, which I think is the last one on this particular one, is how many grams of this sodium azide product, NaN3, are theoretically obtained? Okay? So we are going to, because we know that our N2O is a limiting reactant, we're going to start with that in this problem. All right, so now that we're just going to do the same thing as before, we're going to calculate an amount of product, but we have to start with our limiting reactant. We have 3 different reactants we could start with, but we have to start with the one that's limiting to get this correct. And so the grams of our product, sodium azide, that form, we can either start with the mass or the moles of limiting reactant. We already calculated moles, so let's start with that, saves us a step. So we have 0.119 moles of N2O, and now we can use, because we're in moles of limiting reactant, we can use coefficients in the balanced equation to figure out how many moles of the product form. So we want moles of N2O in the bottom, moles of NaN3 in the numerator, and we're going to put the respective coefficients in front of those, a coefficient of 1 for NaN3, a coefficient of 3 for N2O. So that's how many moles of that product form, and then to get the mass of the product, we use its molar mass, which is given here as 65.01. So 65.01 grams of sodium azide in 1 mole. And that comes out to 2.58 grams. So this is how much of that product we could potentially get. And that would line up with choice D then. Okay? So any questions on those topics? We've done a couple examples. I think that illustrates all the concepts we need. All right, so if there's nothing else to clarify, I'll move on then to one other stoichiometry topic that we need to cover, which is the concept of yield, which is a very practical concern, because when you're doing chemical reactions in a lab, you do need to think about these 3 things when you're doing the reaction and trying to understand some things about it. All right, so we have 3 definitions to give. So theoretical yield is the maximum amount of product that can form. So typically, when we're talking about yield, we're doing it in the context of 1 or more of the products. And the theoretical yield is the maximum amount of a product that can form if all of the limiting reactant is consumed. Now, another way of understanding this quantity theoretically, this actually isn't something new for us, it's just perhaps a new terminology. This is the amount of product that you calculate that could form in the reaction. So the last 2 problems we did, in both cases we calculated how many grams of one of the product can form. That would be the theoretical yield. That's the ideal amount of product that can form if all the limiting reactant is consumed. So whatever you calculate using stoichiometry would be a theoretical yield. Now, the other thing that's important, though, is that when you're doing a chemical reaction in the lab, very rarely do you actually get the theoretical yield as the amount of product that you obtain. So the actual yield is the amount of product that you obtain experimentally. There's no real way to calculate this. This is an experimental number that you would measure when doing a chemical reaction. As usual, I have a very faint idea of what you guys actually do in the lab portion of this course, which is my fault, but also because I don't teach the lab portion. So I don't know if you guys do any chemical synthesis in the lab, but if you do, you would measure then how much product you get from a chemical reaction, and that's going to be the actual yield. And in most cases, this is less than the theoretical yield for a few possible reasons. One is experimental losses. So you don't, even if all the product forms, you don't always collect all of it. Either, I mean, if you have ham hands, if you have 5 thumbs or whatever, you might drop some of it. That's obviously avoidable in most cases. But even in some cases, you're doing the reaction in a glass container, and some of the solid product sticks to the glass, and no matter how hard you try, you can't get it out. Or if you want to isolate the product by crystallizing it from a solution, sometimes some of it just stays dissolved no matter what you do. So there's experimental losses, which are just limitations of how you do the experiment, that sometimes not all the product that forms can easily be collected. So that's what we would call an experimental loss. Another possible reason that the actual yield is less than the theoretical yield is because of what are called side reactions. So sometimes 2 or more of the reactants that are present can react in other ways. They can form other products besides the one you want. Or sometimes one of the products can start reacting with one of the reactants as it forms. And so these are called side reactions. These are basically other unwanted chemical reactions that are happening at the same time. Again, no easy way in many cases to predict whether this will happen or not, especially at the level of knowledge we have now, but you'll start learning about these things more in organic chemistry. And then another reason, which is a topic you'll cover in more detail in the second semester of general chemistry, Chem 1332, is that in some cases the reaction just doesn't go to completion. This is a situation referred to sometimes as equilibrium, where basically the reactants don't completely react with each other. You're going to get some product, but you're going to have some reactants left over, and they're going to sort of stay there and not go all the way until the reactants are completely gone. So there's a few reasons. We're not too terribly concerned with this in this course of why you don't get the theoretical yield, but these are the reasons, and basically the idea is that the actual yield is in almost every case going to be less. And then the way that we would quantify this is with percent yield. So to figure out how efficient or how effective was the reaction we did, we would take the actual yield and divide it by the theoretical yield and then multiply by 100 to get a percentage. And this number, if you do it correctly, will always be less than or equal to 100. So 100% yield is the best you can do. That's when you've gotten exactly the amount of product that the theoretical yield predicts you would get. Anything less than that is usually what happens in a real experiment, and those are all possible. But if you get greater than 100% yield, then something went haywire in the calculation. All right, and as I said, there's no way to calculate the actual yield, and unless the only time you would actually solve for actual yield is in some cases, if we give you the percent yield, you can calculate theoretical yield and then do some algebra to figure out what the actual yield is. So that's the only time you'd actually be solving for actual yield, is basically if that's your only unknown. But there's no way from first principles, from the information about limiting reactants and all that stuff, to figure out what the actual yield will be. That's totally an experimental quantity, and in many cases varies from person to person, from experiment to experiment. All right, so let's see how this works in a couple examples. So this ugly looking gray powder tungsten WCl6, tungsten 6 chloride, can be prepared directly by taking the 2 elements, tungsten and chlorine gas, W and Cl2, and then it's a fairly dangerous reaction, but they will react in this way. So someone combines 5 grams of tungsten, 6.75 grams of chlorine, and at the end of the reaction obtains 5.92 grams of WCl6. What is the percent yield for this reaction? So the first thing in these types of problems is to identify the information we're given. So we have amounts of both reactants, so that should trigger an alarm bell in our head that we need to figure out which one of those is a limiting reactant. And then it says at the end of the reaction obtains 5.92 grams of the product. So if we're telling you in the problem how much of the product you're obtaining, this would be your actual yield, okay? So we're telling you this is the actual yield of WCl6 you get. We want to figure out what's the percent yield. And so in order to do that, remember that the percent yield is the ratio of the actual yield to the theoretical yield times 100, so we need to figure out what the theoretical yield of this reaction would be. All right, so the steps are going to be the same as we've now done before, which is we first need a balanced equation. So we have W plus Cl2 Those are the two reactants, and they're going to form the product, which is WCl6. So we need to make sure this is balanced. We have 6 chlorines on the right, so we need to put a coefficient of 3 to also have 6 chlorines on the left. So a fairly simple equation in this case, W plus 3Cl2 going to WCl6. But if you're not given a chemical equation, anytime you have a problem involving stoichiometry, make sure that you write out a balanced equation before you try to do anything else. All right, and then we're going to follow the same set of steps we did before. So what we want is the percent yield. So let's keep in mind what we're looking for at the beginning of the problem. We need the actual yield and the theoretical yield. And we multiply that by 100, okay? This was given to us already. The actual yield is 5.92 grams. That's how much we actually obtained. So we just need to follow the steps needed to calculate the theoretical yield to be able to figure out what the percent yield is at the end. And remember that the theoretical yield is just the amount that we would get from doing stoichiometry. So from figuring out what the limiting reactant is and then doing all the mole conversions and so on, that would give us our theoretical yield. So we're going to follow the same steps as before. We're going to first figure out what the limiting reactant is. So moles of each reactant, we have 5 grams of tungsten, W. The moles of tungsten, we're going to use its atomic mass. So this is going to look very repetitive with what we did before already today. All right, so we get 0.0272 moles of tungsten W, and then the stoichiometric ratio is going to be that number divided by the coefficient. The coefficient for W is 1, so it's the same number. All right, and then we have to figure out the same quantity for Cl2, figure out if it's bigger or smaller to determine which of these is a limiting reactant. So for Cl2, we told that we have 6.75 grams. And the molar mass of Cl2 was given. In this lecture, I gave you all the molar masses just to save time. So on test questions, they may or may not be given to you, so make sure you know how to figure out molar mass. But in a lot of cases, they will be given to you to help you save time. All right, so we have molar masses given, so we're just going to use those to figure out moles of each. So for chlorine, we get 0.0952, but then we have to figure out the ratio by dividing that number by the coefficient, which is 3. So coefficient for Cl2 in the balance equation is 3. Dividing those, we get 0.0317. So again, they're not too different from each other, but this number is clearly smaller, so that's going to be our limiting reactant, okay? So in order to figure out the theoretical yield, we do need to know what the limiting reactant is, because the theoretical yield is determined by how much limiting reactant we have. And so now we can do the calculation to get that. All right, so to remind ourselves, this is the balanced equation, which we still need. And then we can figure out the theoretical yield of WCl6. So whenever we do a calculation like this, that gives us the theoretical amount. So we're going to start with moles of limiting reagent. In the previous step, we figured out that there's 0.0272 moles of tungsten as our limiting reagent. And then we're going to use mole ratios with the product to figure out how much product forms. And so it's just a 1-to-1 ratio. Both WCl6 and W have coefficients of 1. So 1 mole of WCl6 forms for every mole of W, tungsten, that reacts. And then finally, to figure out the theoretical mass of product, we're going to use its molar mass, which is 396.54. So 396.54 grams of WCl6 per mole. And the number that we get is 10.8 grams. And that number, as I said, represents the theoretical yield. All right. So that's going to be the theoretical yield. And then finally, we can calculate percent yield by just using the definition of percent yield as we introduced at the beginning of the problem. So percent yield is actual divided by theoretical times 100. And so those numbers, again, the number that we're given in the problem, 5.92 grams, that's the actual yield of WCl6, the amount that we obtained experimentally. The theoretical yield is what we just calculated using stoichiometry. So the maximum amount that we could get if all the limiting reactant is consumed is 10.8 grams. Then we divide those two, multiply by 100, so we get a percent yield of 54.8%. Okay? Now, the question might be percolating, is that good or bad? The answer really depends on what reaction you're doing. So in some chemical reactions that you do in a lab, you would throw a celebration over a 54% yield. In other cases, that's pretty pitiful. So it really depends. Some reactions work better than others, and this particular one I've never done, so I don't know if 54.8% yield will be good or not, but that's what we get from the information in the problem. All right, so any questions on percent yield? Yep.
How do you find 10.8 grams? How do you find 8.8 grams?
That's the number we calculated in this step here. So
step by step?
Yeah, so we're doing it step by step. And so when you want to get the theoretical yield, you're typically going to get that by using stoichiometry, by figuring out what the limiting reactant is and then doing all the steps, mole conversions and all that to figure out how much product could potentially form. And then you're going to use that number in this calculation to get the percent yield. All right, anything else? All right, so I think that's it. We're done with chapter 5, so if there's any last lingering questions on stoichiometry, get them out now.
One last thing.
Yep.
On the output question, some of the problems are going to be more like a lot of multi-step questions to find out the percent yield.
I mean, it wouldn't be more steps than this. This is the steps that you need to find percent yield. I suppose it could be a little bit longer if we gave you 3 reactants and you had to figure out what the limiting reactant is, but that's the only other variation you should be aware of is, as I sort of mentioned already, we could ask you to solve for the actual yield if we give you the percent yield, and then you also calculate the theoretical yield in the same way. So in some cases, this will be unknown, this will be given, and you just have to solve for it using a little bit of algebra. So that's really the only variation that I didn't cover, but it's the same set of steps, just a little bit different at the end, because in that case, your unknown quantity is the actual yield instead of the percent yield. So it's really the same series of steps that you're always going to be using, and as you do the homework problems, you'll sort of see the different ways we can ask you to do this, but there's not too many variations on this, okay? All right, anything else? Last questions. All right, so for chapter 6, there's going to be, as we'll see towards the end, a lot of stoichiometry involved as well, but what we're talking about in chapter 6 is reactions that happen in aqueous solution, okay? So we're going to start out with some definitions. So I think the way that I'm going to cover this is a little bit different than your textbook. So again, just to warn you, if you're religiously following the textbook, there are some things I'll do differently. So I think the way that your book does it is, what we're going to do in this chapter is we're going to introduce, I guess, 3 different types of chemical reactions that happen in aqueous solution and talk about, how to classify them, how to make some predictions about them and some features of them and so on. And I think what the book does is it sort of does stoichiometry at each of those stages. Like, it's going to cover one type of reaction and then do some stoichiometry examples, cover another type of reaction, do some stoichiometry examples. The way that I have this organized is I'll just do all the stoichiometry at the end, because really for all 3 types of reactions that happen in solution, the types of concepts and the types of operations you use to do stoichiometry for those is all the same. So I don't feel like there's any reason to break it up and cover it 3 separate times. We're just going to cover the 3 types of reactions, and then at the end we'll come back and talk about stoichiometry in the context of these types of chemical reactions. All right, but what we're doing in this chapter, as I said, are chemical reactions that happen in solution. So let's define what a solution is. We probably are at least a little bit familiar with this. So remember, in chemistry, there's 2 types of mixtures, homogeneous and heterogeneous. And so solution is sort of a synonym for homogeneous mixture. So it involves 2 or more substances. So it's not a pure substance anymore, it's a mixture. And what defines it as homogeneous is that it's what we would call a single phase. So you cannot tell by looking at it that you have 2 or more things mixed together. It looks like one substance, but there's actually more than one thing mixed together in there. The type that we're going to talk about primarily, and the type that we usually deal with in chemistry, are going to be solutions that involve a liquid as the major component. Okay? Now you can have solutions of any of the phases of matter, So you would have a solid solution is what we would call in many cases an alloy. So if you've heard of alloys, which are basically mixtures of metals, that would be considered a solid solution. You can also technically, gas can be in a solution, like the air that we breathe is a solution. It's a mixture of many different gases, and you can't just tell by looking at the air that there's more than one gas in there. But the most common type of solution, and the type that we'll deal with in this chapter, are going to involve liquids as the major component. All right, so there's some common examples of solution that I've already, in many cases, mentioned. So salt water is a very common example of a solution. Most beverages are solutions. If they're fizzy, if they have carbonation, they're not really a solution because you can see the gas bubbles mixed in with the liquid. But if it's a flat beverage, it's going to be typically a solution. Air, as we said, is a solution. Gasoline is a solution. Actually, gasoline is a mixture of several different things. So all of these are examples of solutions in our everyday life. And then when we have a solution, we can define the two components, sometimes more than two components, and we can classify them as either solute or solvent. So typically speaking, the solute is the minor component. In some cases, it's a little bit ambiguous what's the solute and the solvent if they're present in equal or nearly equal amounts. But if it's very clear that there's a minor and a major component, the minor component is referred to as the solute. And this is basically what is dissolved to make the solution. So in salt water, salt, primarily NaCl, is the solute, and the water is the other part, which is the solvent that we'll define here in a second. So it's typically the minor part is the thing that is dissolved to make the solution. And then the solvent is the major component. And again, in types of solutions we're going to talk about in this course, the solvent will be a liquid. So usually the term solute and solvent is used for liquid solutions where the solute is the minor component that's dissolved, and the solvent is the liquid that you're using to dissolve it. So the solvent is the substance that does the dissolving. It dissolves the other substance. And even though the definitions are more general than this, in context, the solvent is almost always a liquid. And in the types of reaction we're going to talk about in this course, it's going to usually be water. When you get to organic chemistry, water is pretty much not used at all, as it turns out. But for the types of reactions we're going to talk about in general chemistry, water is usually our solvent we're talking about. And then the word that we use to describe a solution that's in water is aqueous. So that term aqueous, which is, I think I already mentioned it as being the major theme of this chapter, aqueous means dissolved in water. So if you have aqueous hydrochloric acid, that means you have hydrochloric acid dissolved in water. Or aqueous sodium chloride would be sodium chloride salt dissolved in water. So that's what the word aqueous means. Now we have to talk a little bit more about what does it actually mean to dissolve something. So I think you guys have at least a general context of what that means. You've all probably you've all probably made salt water before, dissolved salt in water or sugar in water. You've probably made non-alcoholic beverages before. And so you know what the process of dissolving involves, which is mixing two things together, until they sort of combine homogeneously. But let's talk about it a little bit at a molecular level of what it refers to when we're dissolving something. So the first thing to understand is why does water dissolve so many things? And the reason is because it's polar. So let's review a little bit about the polarity of water, a topic back from chapter 4 just a little bit ago. And so the first thing is to recognize that in water we have hydrogen and oxygen. And oxygen is significantly more electronegative than hydrogen. So this is all reviewed, but just to remind you of what it means to be polar. The other thing that's important, again, in addition to electronegativity differences, is the shape of the molecule. That's especially what we talked about in chapter 4. Water has a bent shape. It's AX2E2 in the VSEPR terms. And so what that means is that the bond dipoles between hydrogen and oxygen, again, oxygen being more electronegative than hydrogen, meaning that you're going to have a polarity set up there, those are not going to be able to cancel out because of the bent shape. And then what ends up in water then is you have negative and positive poles. That's what we mean by a dipole, is that you have a sort of a separation of charge, not a complete separation in this case because it's a polar covalent molecule, but you have partial positive and partial negative charges on each end of the molecule. So there's a lot of different depictions of this, but this one down here shows that the net dipole in water points up towards the oxygen. So basically you're going to have, and then this colored picture here red means negative charge, blue means positive charge, you have a concentration of negative charge at the oxygen and a concentration of positive charge near the hydrogens. Now what this allows water to do then is it can dissolve things, because if it's dissolving either an ionic compound or another polar substance, you basically have opposite charges attracting to each other. So the negative part of water, the oxygen, the negative dipole, is going to be attracted to the cations in an ionic compound, and the positive end of water, where the hydrogens are, that positive end is going to be attracted to the anions, and that's going to result in the dissolution process. So to look a little bit at how this looks at a molecular level, I have a couple of videos linked here, and I'll pull them up for you. Oh crap, I closed that by accident. Had them loaded up, but I think hopefully, yes, this is the first one. So we're going to talk about what happens when we dissolve ionic and covalent compounds in water. So there's some key differences here. So one thing we'll learn later on in this course is that when you have an ionic compound like sodium chloride, you basically just have these alternating arrangements of the positive and negative ions. Okay, so this is what sodium chloride looks like. It's sort of a block-shaped structure with alternating plus and minus charges. And so what happens then, assuming this video works for us, all right, so this is presented as an interactive video, but it's not actually interactive, so you just have to watch it. If I had the sound on, they'd be like, click the button, and you can't actually click anything, it's just a video. But anyway, so when you dissolve salt in water, that's what it looks like macroscopically, and you guys are familiar with that, but let's see what happens at the molecular level. So you have your block of sodium chloride. This is painfully slow. So, all right, there you go, finally. All right, so you have your block of sodium chloride, and basically the water molecules are going to surround the individual ions and pull them apart from the bulk structure. So you're going to separate the positive and negative ions from each other. And if you look closely, you'll see that when one of the negative ions, which is chloride, gets dissolved, you'll see that the positive end of water, the hydrogens, sort of line up around that and surround it. And then the opposite is true for sodium. If you follow that one there, you'll see that the oxygens, which have the negative dipole, surround themselves around the positive cations. And so this process basically goes on, and you're going to pull all the individual ions into the bulk liquid solution and separate them from each other. Now, when you dissolve a covalent compound in water, so CH3OH, which is called methanol, is another liquid, and you can dissolve that in water. So this is showing if you just add a few drops of methanol to water, they will mix together completely and form still a clear, colorless solution. So it's still a homogeneous mixture. But in this case, when you have a covalent compound, you're not going to break the molecules apart. So you still have in methanol, it's a polar molecule, so you have a partial negative near oxygen, a partial positive near the hydrogen that's bonded to it. But when water molecules come in, they're not going to actually destroy the molecule like they did before. They're going to just surround it where the negative and positive ends are going to line up with each other, and they're going to sort of surround it and bring it into solution. So that's what this is going to show. You have initially all the methanol molecules are sort of associated with each other, but then when you put it into water, the water molecules are going to surround each of the CH3OH molecules, and you can see once again that the positive and negative ends are sort of lining up with each other. And so you're going to have clusters of water molecules that surround each of the solutes and bring it into the solution, but they're not going to break it apart. They're not going to have any bond breakage associated with that. So that's the key difference between dissolving ionic and a covalent compound. With an ionic compound, you separate the ions from each other and they go into solution separately. When you have a covalent compound, the molecules of the covalent compound stay together even as it dissolves into the liquid solution. All right, so let's summarize those key points there. So with ionic compounds, which is the first part of the video, in that case it was showing sodium chloride, the key part is that the ions, the individual ions that make up the compound, separate when you dissolve them into solution. Okay? So you no longer have sodium and chloride associated with each other. You have separate sodium ions that are surrounded by water molecules and separate chloride ions surrounded by water molecules. In contrast, when a covalent compound dissolves in water, you're not going to have any breaking of bonds. Now, the one exception that we'll talk about a little bit is acids are technically a covalent compound, and they do separate into ions, but for a typical covalent compound, a regular polar covalent compound that's not an acid, it will dissolve in water in many cases, but it won't separate, it won't break any bonds or dissociate in any way. Okay? So that's how things dissolve. And then the other thing that I want to talk about a little bit is some properties of solutions. So if you guys think that I'm weird. Wait till you get a load of this guy. So he's going to do some experiments for you. So he's going to do some experiments with different types of solutions. So he has all different things dissolved in water. What he's going to test is whether these solutions conduct electricity. So he has basically two electrodes here that are not connected to each other. He's going to attempt to use each liquid to connect the circuit. And so with tap water, you see the light bulb lights up, although not particularly bright. If he goes from pure water to still water, nothing happens. So there's no electroconductivity in that case. Sodium chloride dissolved in water, we get bright light bulbs, so clearly it's conducting electricity. Hydrochloric acid, a strong acid, conducts electricity. Sodium hydroxide, another ionic compound, which we'll learn later, is also classified as a base, conducts electricity. So we see a lot of these solutions conduct, but now he has a solution of sugar in water, and nothing happens. And then he has vinegar, which is another acid, this time a weak acid, as we'll learn a little bit later. Conducts electricity, but if you can tell, maybe not as strongly as some of the other ones. This is ethanol, which is another type of alcohol, like the type that you will drink when you're old enough. And that one doesn't conduct electricity at all. And then this is barium sulfate. This is an ionic compound, but it doesn't dissolve in water, as you see. It's sort of a heterogeneous mixture. And in this case, when the compound's not dissolved in water, you don't get any conductivity in the solution. All right, so that's some experiments with different types of solutions. So let's summarize the results there and then get us into some definitions that are related to that. All right, so the key thing that we saw is that if you have an ionic compound dissolved in water, those solutions will conduct electricity. And they conduct it very well, as we saw. We got very bright light bulb lit up. And then also, I should also mention acids as well, which we'll give you more information about on the next slide. But those two types of compounds, when they're dissolved, they conduct electricity. We saw that if we dissolve a covalent compound, regular covalent compound like sugar, or if we just had pure water or pure ethanol with no ions dissolved, there was no electroconductivity. And then what we call a solution that conducts electricity is an electrolyte solution, okay? So any solution that conducts electricity, which as we said is typically ones that involve ionic compounds or acids, those are going to be referred to as electrolyte solutions. All right. Electrolyte also has a sort of nutritional context that you might be familiar with, but in this chemistry sense, it means a solution that conducts electricity, okay? So there are three types of solutions then that we can classify: strong electrolyte, weak electrolyte, or non-electrolyte. And basically whether the solution is going to fall into these categories depends on what kind of compound is dissolved in that solution. So strong electrolytes are going to be ones where when you dissolve the compound in water, ions break up completely. So you need ions in solution to be able to conduct electricity. And so strong electrolytes are going to be soluble ionic compounds that dissolve in water will all be classified as strong electrolytes. Or strong acids. Now we're going to learn later on in this course what an acid is and how it reacts and how to classify strong versus weak. Strong versus weak you're going to get a lot more of in Chem 2 more than this course. But the strong acids that we should be familiar with would be hydrochloric acid, HNO3, nitric acid, H2SO4, which is sulfuric acid, and perchloric acid, HClO4. There are probably others out there, but these five are the most common. And basically what happens, as we'll talk about a little bit later on, when you dissolve these acids in water, they completely separate into H+ ions. So remember, the acid is hydrogen combined with an anion. And so these five acids, when you dissolve them, they completely separate into H+ ions plus whatever anion is associated with that. So HCl, when you dissolve it in water, gives you H+ and Cl-. If you have a lot of ions in solution, your solution will be a strong electrolyte, okay? And the key thing is that these strong electrolyte solutions, they conduct electricity really well. Now, we also have solutions that are classified as weak electrolytes, so they still conduct electricity, but not as well. And these are compounds, these are going to be made of compounds that partially break down into ions, right? Now, again, this concept of partially breaking down into ions is not going to be something we deal a lot with in this course because it's a lot more complicated, something you'll get to in Chem 2. But because the compound only partially breaks down into ions, you don't have a lot of ions in solution, and so they only weakly conduct electricity. The example that you saw in the video, maybe it wasn't totally obvious from the video, it was acetic acid, or what you called vinegar, which is just a solution of acetic acid. That would be what we call a weak electrolyte. So really the only class of compounds that, for our purposes, we're going to classify as a weak electrolyte would be weak acids, which is basically any other acid except for the ones that I listed above. So hydrofluoric acid. I guess I should also put, I think I left some out here. Sorry. HBr and HI, which are related to HCl. So those three of the halogen acids, but then all other acids would be weak. So HF, H3PO4, HNO2, like all these, there's a lot of different weak acids. So basically anything that's not from this list we would assume is weak. Or weak bases. We're going to talk about, again, acids and bases later on, so this won't make perfect sense till now, but the only weak base that we need to know about is NH3. We'll talk about it more later on. It's the only weak base we'll deal with in this course. So those ones are called weak electrolytes. When you dissolve these in water, they do not completely separate into ions, and so you don't get a lot of ions in solution, but you get some, so you're going to still have weak electrical conductivity. And then non-electrolytes are ones that have no electrical conductivity, and so we saw that pure water by itself was non-electrolyte. Electrical. We saw that pure water was a non-electrolyte, and then certain compounds dissolved in water, sugar, ethanol, and so on, those are basically covalent compounds that are not acids or bases. All right, and there's a lot of things that could fall into this category. The two most common that we'll see in this course would be things like sugar, so sucrose, glucose, things like that. Those are all non-electrolytes when you dissolve them in water. Or alcohols, so that would be like ethanol, which is CH3, CH2, OH, or just methanol, which is CH3OH. Basically, alcohols they have an OH group on them and something else attached to the other side. They're kind of like water, but you replace one of the hydrogens in water with some other organic chain. But these are all non-electrolytes. So when you dissolve them in water, the water will surround the molecules, but they won't separate it into ions, so you're not going to get any electrical conductivity. Okay, so those are the three categories of solutions, and that's sort of one of the early concepts we want you to know. And so what this allows us to do then is talk about what happens when we dissolve a compound in water and how that relates then to the moles that are in solution. So if we take silver nitrate and dissolve it in water, we want to know how many moles of ions are present when 3 grams of this dissolves in water. Okay? So what we can think about then is if we have silver 1 nitrate, we need the formula for that, so it's going to be AgNO3 plus 1 on silver minus 1 on nitrate, so you need 1 of each to balance the charge. So what happens when we dissolve this in water? As a solid, it looks a lot like salt, just a crystalline white ionic compound. But when we add this to water, what's going to happen is, as we said, because this is a soluble ionic compound, when we put it in water and dissolve it, it's going to break up into its individual ions. So you're going to get the 2 ions that make this up are Ag plus, silver 1, and we're going to put next to that a little symbol AQ, indicating that it's now dissolved in water. So in chemical equations, if you see AQ in parentheses, that means aqueous, which means dissolved in water. And then the other ion is NO3 minus. So when we dissolve this in water, it separates into ions, and so this is sort of the process we want to think about for this question. Because what this question is asking us is how many moles of ions, not one specific ion or another, but how many total moles of ions. And so to figure this out, what we have to do is first figure out how many moles of silver nitrate we're dissolving. So we have 3 grams of silver nitrate, and we can use molar mass to figure out how many moles that is. So we're going to divide by its molar mass, which is 169.87. But that, again, represents the moles of AgNO3 that we're dissolving. If we want the moles of ions in the solution, we have to keep in mind that when we dissolve this in water, for every 1 mole of AgNO3 that we dissolve, we get 1 mole of Ag plus and 1 mole of NO3 minus, meaning that in total, we're going to get 2 moles of ions for every mole that we dissolve, okay? because we're looking here for total moles of ions, so we're going to get one of each, one positive ion, one negative ion, a total of 2 moles of ions for every 1 mole that we dissolve. And so the last step there to figure out how many moles of ions there are is to use that ratio. 2 moles of ions are going to dissolve for every 1 mole of AgNO3. And so this factor here, 2 over 1, depends on the formula of the compound. So if the compound had more than 2 ions in the formula, then this would be some number other than 2. But whenever you dissolve an ionic compound in water, it's going to separate into its individual ions. And so in this case, you're going to get 2 ions for every mole that you dissolve. All right, and so that gives us moles of ions. So this last step here would be the one that is most commonly forgotten. And what we get is 0.0353 moles, okay? So that just allows us to extend our mole relationships a little bit, now understanding what happens when an ionic compound dissolves in water, if we want to talk about how many ions there are. Yes?
Basically, it may have the right to have like 3 moles ions. That's sometimes the solution to sometimes you can be seen as.
Sorry, I'm having a hard time hearing you because people are talking. Please quiet down so I can hear this question.
That means that the 3 moles that means 3 compounds. If it's 3 moles like signifying something on the.
Well, in this case, it's 2 moles because we're only forming Ag plus and NO3 minus. But if it was, it would be 3 if it was something like calcium chloride.
Yeah.
So when you dissolve this in water, you're going to get Ca2 plus and then 2 Cl minuses. So in total, you would get 3 moles of ions because you have 1 calcium and 2 chlorides for every mole that you dissolve. So what factor you're going to multiply by here is going to depend on the formula of the compound and how many ions are contained in that formula. Because whenever you dissolve it in water, it's going to separate into all of the ions that it has in the formula. All right, so that's just a little bit of an aside to help you understand that relationship that'll come up at times in different problems we do. The last thing that I want to introduce today is molarity, which is a new relationship involving moles. So molarity is a property of a solution, and it tells us a concentration of that solution. So molarity is a concentration unit. There are other concentration units that you will come across in various contexts, but not so much in this course. But the one we're going to use all the time in this chapter is molarity. And the definition of molarity is moles of solute divided by liters of solution. All right, and I want you to pay close attention to the precise definition of this of molarity because it's per liter of solution, not liters of solvent. All right, so if you dissolve some amount of solute in 1 liter of water, you won't necessarily get 1 liter of the solution. The volume sometimes changes as the substance dissolves. It can either expand a little bit or contract a little bit. So the definition of molarity is moles of solute per liter of solution. So this is what the denominator is here. That's not going to be important most of the time, but it is for keeping the definition straight, and for certain types of problems we'll do that is important to realize. The abbreviation for molarity is just capital M. And then, so as an example of molarity, let's say we prepare a solution that has 2 moles of solute for every 1 liter of solution. We would say that this is a 2.0 capital M solution. The way we would say that is 2.0 molar solution, or the molarity of this solution is 2.0. Now, one nice thing about molarity is that it's what we would call an intrinsic property of the solution. It doesn't matter how much of the solution you have, the molarity will be the same. So if we have a 2.0 molar solution, let's say of salt water, sodium chloride in water, if you have 1 drop of that solution, the molarity is 2.0. If you have a gallon of that solution, the molarity is 2.0. If you have an ocean of that solution, the molarity is still 2.0. So it's an intrinsic property because it's a ratio of 2 quantities, moles per liter. So what we're also going to start to recognize now, although we won't use it so much until the next lecture, is that we can start to think of this as a conversion factor, moles per liter. So now if we want to convert between moles and volume of solution, we have a way of doing that. We're going to talk about that a lot next time. But let's just end with an example of how to calculate molarity. So this is sulfuric acid. If you add sulfuric acid to pretty much anything that has carbon in it, it turns black and smokes, and it's pretty awful. So I would suggest not adding sulfuric acid to your skin for that reason. This is just like, I think, cotton or sugar or something that you add a sulfuric acid to. But it's pretty nasty stuff. It'll destroy pretty much any organic compound. But that's not so important for this problem. What we want to do is calculate the molarity of solution prepared by dissolving 15 grams of H2SO4, sulfuric acid, in enough water to form 200 milliliters of solution. So again, molarity is defined per volume of solution, so you need to know how much solution you have to be able to calculate the molarity accurately. Okay? In most cases, if you were to dissolve 15 grams of sulfuric acid in 200 milliliters of water, you would get pretty close to 200 milliliters of solution. So the molarity is not too different in that case. But in reality, if you want to accurately calculate molarity, you need to know the volume of the solution that you have. All right, so for calculating molarity, the two things we need are moles of solute and liters of solution. And again, keep in mind that the denominator in this always has to be in liters. So that's the unit that we need for the denominator is liters. And so let's just get these two quantities. We need two things, so we need the two quantities. So the moles of sulfuric acid, H2SO4, it's just going to be a simple mass to mole calculation. We know the grams of H2SO4, we know the molar mass, and so we're going to do the same mass to mole calculation that we've been doing dozens of times in the last two classes here. So 15 grams of H2SO4, and then 1 mole has a mass of 98.1 grams. So we're just going to use the molar mass, as we always do, to convert grams into moles. And so that's 0.153 moles. All right. And then if we want to find the liters of solution, this is where we have to be a little bit careful with units, because it's probably more common in chemistry to use milliliters as the unit of measure, because liter is a pretty big volume. You don't usually work with that amount on a laboratory scale, not often anyway. So we're going to give you a lot of times volumes in milliliters, so you have to convert to liters. So remember that milli means 10 to the minus 3. So if you want to convert into liters, there's going to be 1 liter per 1,000 milliliters. And so you're going to have 0.200 liters. Okay? So we need to make sure that our volume unit is in liters to be able to calculate molarity. And now we have the two numbers we need. We have moles of solute, we have liters of solution, and we're just going to divide the two. 0.153 moles divided by 0.200 liters, and the number we get is 0.765 capital M molar. Okay? And so that's the molarity of this solution, meaning we have 0.765 moles of solute per liter. All right, so that's how we calculate molarity. Next time we're going to see some examples of how we use molarity as a conversion factor involving volumes of solution in moles, and then work our way into different types of chemical reactions that happen in aqueous solution, which is the major focus of this chapter.